Magandang umaga. So what we have here, I'm sharing with you my screen, and the topic is inverses. Today's topic would be the last part of chapter 4. So that would be on inverses, and the first part of chapter 5, which is the rank of a matrix. Okay, so I think last time we did had a joint discussion with my Econ 106B class, and I think that we finished until the chapter on transpose. Okay, so now we go to the concept of inverse. Now, the topic of inverse class is, so the inverse of an n by n matrix is just another n by n matrix. The inverse of A is written as A raised to the power of -1, and it is pronounced as A inverse. So when I say inverse of A, I'm just referring to the inverse. When I say inverse of A, I'm just referring to A inverse, meaning A raised to the power of -1. Okay, and the fundamental property is just simple. When you think about an inverse class, you just need to multiply A and then multiply it to A inverse, and you're back to where you started. Again, the fundamental property is just simple, class. All you need to do is to look for A inverse and then use that one later on to multiply it to a constant where you can get a solution value, which is x star. Okay. Now, what is the mathematical proof, or what is the proof that we have to say that getting the value for x star is just equal to A inverse multiplied to a constant or a vector? Now, again, every time if we have a system of linear equations, class, we rewrite it, or we wrote it in a way that it is appropriate for matrix notation. So we write it in a form AX is equal to D. So just to review, A is just your coefficient, X is your vectors, or your column vector, or your unknowns, and D are your constants. So if you have a linear system of equations, you transform it in that way, AS is equal to D. Now, if you will be solving for the unknowns there, if you're solving for X there, we just need to get the inverse of A, which is A inverse, because multiplying or getting getting A inverse, you multiply it in both sides of the equation. And so for this side as well, and also the right side. And what will happen, class, if you multiply A to A inverse, you will get the product that is just equal to the identity matrix. So again, multiplying A inverse to the original matrix, you will result to, or you will end up to I, or to an identity matrix. Your product would be an identity matrix. So simplifying, this will now be equal to Ix equal to A inverse multiplied to the vector, or multiplied to the constants. Simplifying as well, because again, identity matrix multiplied to another matrix, you will end up to the original, or where you started, or where to the original matrix, which is equal to X here. So in that case, simplifying this, it will turn that X is equal to A inverse multiplied by T vector. So later on, class, once we're solving linear system of equations, we can just use this idea of inverse to get the values of X. Again, why is X star equal to A inverse multiplied by a vector? The reason is this one. Okay. Question. How do we perform this? Now, before doing so, class, we will need to have a series of discussion. We will still have a series of, let's just say, sections or sections before arriving to this one here. We will still need to discuss the properties. We will look at the conditions that should be met in order to get an inverse of the matrix. We will also need to have a concept which we call determinant to help us with getting the inverse. But just an overview of the whole process that we're trying to do here is, again, this is how it would look like later on. Okay, so again, rewriting the linear system of equations into this notation, then going through some processes, we get to get an inverse, and you get and then getting the value for x. So again, this might be a bit disorienting at first, but I assure you, class, understanding it in a step-by-step process would allow you to fully comprehend and fully understand how the idea here. But if you're confused, always just remember that we are trying to solve for x here. Okay. Now for this next slide, here are some of the important things to remember. Number one, or in this bullet, not all matrices have inverses. Now, sa discussion on transpose, class, pag sinasabing transpose, immediately, ano siya, it's we're just interchanging the dimensions of the rows and columns. So you are assured that that matrix will have a transpose. In this case naman, not all matrices have inverses, because again, there are conditions that has to be met in order to get an inverse of that matrix. And one condition, which will we'll go back to a later time, would be the necessary condition of squareness. So it should be a square, it should be an n by n. Okay, but this again, so just support the idea, just to support the argument that not all matrices have inverses. Okay, I hope that is clear. Now the second one, class, is an inverse is impossible when ax is 0 and x is non-zero. So the A inverse there would have to get back from ax equal to 0 to x. So that just means that no matrix can multiply that 0 vector ax and produce a non-zero vector x. Okay, but just to establish, our goal here is to define the inverse matrix and compute it and use it when A inverse exists, and to understand which matrices don't have inverses. Now, you don't have to remember all these things, class. You don't have to remember that it is impossible to have ax is 0 and x is non-zero, because you need to go back to you will need to parang have to go back to ax is equal to 0 there. It is just not possible. But again, these are some of the things that you will be observing later on once you have an inverse of that matrix. So these are just your guide. Now let's formally outline some of the notes when discussing inverses. Okay, so if A inverse exists, so if A inverse does exist, then the matrix A can be regarded as the inverse of A inverse, just as A inverse is the inverse of A. Plainly, in short, class, it's just telling you that matrix A and A inverse are inverses of each other. Okay, so if you get the inverse of A here, you'll get inverse A inverse. If you get the inverse, if you get A inverse, you'll get A. Okay, so but the idea of this note here is both matrices are inverses of each other if the inverse exists. Second, if the inverse of an n by n matrix is another n by n matrix. So what does this tells us? If A is an n by n, then A inverse must also be an n by n. Otherwise, it cannot be conformable for both pre and post multiplication. The identity matrix produced by the multiplication will also be an n by n. So the reason, class, that kinakailangan natin to also check the dimension, because again, we are doing multiplication here. We're doing matrices matrix multiplication. And one conditional requirement for that is the dimensional requirement that should not be violated. Let's go back to this one, class. What we need to do here to get, what we need to do here for that inverse to exist is dapat we can post and pre-multiply. Okay, so kinakailangan just to go back to that conditional requirement, dimensional requirement, that the lead matrix of the column, the column dimension of the lead matrix should be equal to the row dimension of the lag matrix. Kinakailangan pa rin natin siya to be established and not violated. And aside from that as well, in order to multiply it and to get the product of identity matrix, again, it should be, the identity matrix should be an n by n, or it should be a square, or it should again support the conditional requirement for dimension. Okay, yun lang. Right, let's go to the third one. If an inverse exists, then it is unique. So pag sinasabi nating unique, class, ano siya? It is walang kaparehas, walang iba. Anyway, so if an inverse exists, then it is unique. What am I saying? It just means that the inverse or the matrix A cannot have two different inverses. So pag sinasabi natin na, supposing, class, this is the case na matrix A have two inverses, okay? But again, we know that it's not possible. But let's just say that it's, in this case, it illustrates you why it should not be possible. Okay, so suppose BA is equal to the identity matrix. So we have three different matrices here. We have matrix A, B, and C here, and we said na B is an inverse of A, and so that's why multiplying it to the original matrix A, it would yield an identity matrix. So BA is equal to identity here, and we have also we've also noted that AC is equal to I as well. According to the proof by parenthesis, it would mean that B would be equal to C because, again, we noted that BA is equal to I, AC is equal to I as well. Therefore, BI is equal to IC, and because multiplying it to the identity matrix gives you to the original matrix, it would mean that, or that B is equal to C, which again will be not, because these two matrices are not the same. Okay, therefore, class, there is only matrix A cannot have two different inverses. Or if an inverse exists, it should be unique, or that is unique. Okay. Another thing to take note on this one, class, this shows that it also shows that the left inverse B here, again, we're trying to multiply from the left, and the right inverse C here, multiplying A from the right, which gives us AC is equal to I, must be the same matrix. But then again, they're not the same matrices. And even if coincidentally the matrices are equal, again, this does not support this condition here, that, or this requirement here, that if an inverse exists, then it should be unique. So pag yung inverse ni A si B lang, dapat walang C. That's so one weird to but anyway, I think you get the idea. Okay. Right, let me just. Okay, now let's go to the fourth one. Okay. Satisfying either equation is sufficient to establish the inverse relationship. Satisfying either equation is sufficient to establish the inverse relationship between A and inverse A. Okay, so in this case, this is A inverse A is just equal to I. Okay, now We mentioned earlier, how will we know if B is the inverse of A? The product of these two should be equal to I. So if B is equal to, or if we say that B is the inverse of A, or B is A inverse, then again, it should yield an identity matrix. So in this case, class, we are reverse. We're doing parang we're not doing parang, but we're doing both pre and post multiplication. Here we are doing reverse multiplication, but doing so would still yield the same identity matrix, or the product would be identity matrix. Um, just to note as well, um, this is an exemption to that uh, commutative law of multiplication. Kasi nga, we are treating B as an inverse of A here, and we have proven in some way that it is equal, the product of which would be equal to the identity matrix. Okay, so this is the exception to that rule. Number 5, this again supports this one here. So I'll just read it again. Suppose that there is a non-zero vector x such that ax is equal to 0, then A cannot have an inverse. The reason for this kasi class is that you will need, diba, we're concerned with looking for x here, or we're looking for x star. So if that would be equal to 0, then remember class that this should be equal to D. Okay, there it should be equal to a constant. Okay, so ax is equal to 0. That would mean that A cannot have an inverse. Let's go to the sixth one. Note 6. This just tells us that a 2x2 matrix is invertible, or again, you can get a matrix. You can get an inverse of that matrix if and only if AT minus BC is not zero. So later on, you will be solving this one class. This is what we call determinant. Okay, there are different ways how to get the determinant, but I plan to reserve that discussion after the reading break. But then again, when you have a determinant that is equal to 0, that just means that that matrix cannot have an inverse. Okay, again, later on I'll tell you how to solve a determinant, but for now let's take it as given that if the determinant is equal to 0, then you cannot have an inverse. Okay, so this part of the slide, again, I mentioned last time that we are following a process class from writing a series of equations to arriving to a value for x. Now, this is an overview of what we will do later. So, example, let's just say that we have proven that B is the inverse of A here. So this just tells us that the product should be equal to an identity matrix. So if you have matrix A composing of elements 3, 1, 0, and 2, we also have B there composing of elements 2, -1, 0, and 3. And take note, we have a scalar 1/6 there. Okay. Now, again, if you get the product class, if you get the product of AB there, we can just move later on yung scalar. So it can move into the rear because, again, it is an exception to the rule of commutative law. And so we can go ahead and multiply matrices AB, and then we can get this number, this product here, and multiply it to a scalar, which then would be equal to the identity matrix. So what is just happening here? And also, class, we also do the same. We have pre and post multiplication. This just tells us that, or this establishes that B as the inverse of A and vice versa. The reverse multiplication, and again, as expected, would yield the same identity matrix. So even if you post and pre-multiply it, class, as if the product would be equal to an identity matrix, then we can see that B is inverse. B is the inverse of A, or they are both inverses of each other. Is that clear? Okay, great. So let's discuss the properties. For the first property, again, they're very quite similar with the transpose class. It is straightforward and it is up to you to verify this one. But just I'm telling you that these are those properties that you might be observing later on. No need to memorize this, but again, a helpful way to guide you, especially when looking at or when you're already solving for inverses later. So the first property would tell us that we can read it this way. Okay, so the inverse of the inverse is the original matrix. So if you get the inverse of the inverse matrix, class, you will get the original matrix. Property number 2. So we have the second here, or the second property here states that the inverse of the product is the product of the inverses in reverse order. Again, the inverse of the product is the product of the inverses in reverse order. Property number 3, the inverse of the transpose is the transpose of the inverse. Again, the inverse of the transpose is the transpose of the inverse. Again, class, in this property, we have, or in the statements, we see that the existence of the inverses and the satisfaction of the conformability condition are already presupposed. So again, yung existence of the we have already noted here that we have that an inverse already exists, and at the same time yung conformability condition is not violated. Okay. All right. Now the next slide, it would be the discussion on chapter 5. But I first want to go back here, class. Is there a question about an inverse or what an inverse is? So if I refer, by the way, I say that if matrix B is invertible, or if the matrix B exists, then we can say that A is invertible. So pag sinasabi ko yun, I'm just referring na we can get the inverse of A because B exists. So again, matrix B exists, we can say that A is invertible. Other question, class? What do we mean by an inverse? Or what the use of an inverse, this and that? Okay, let me just clarify some points here. I just want to emphasize again the role of why we're getting an inverse or why we are trying to solve for the inverse class. Um, if the inverse exists, okay, let me use this one. Okay, now in this case, if we're solving for a system of linear equations, we assume that A is a square matrix and we have all other these other ingredients such as the vector variables, we have constants. If you can find the inverse class, which is this one here, of the coefficient matrix A or the original matrix, we know that the right-hand side vector of the constants, or D here, are to multiply the inverse, and then you can have a solution value for every one of your x's. Okay, again, if an inverse exists of an original matrix A, you can just go ahead, multiply it to the vector of constants, and then both of which will give you the solution value for x. Is that clear? Okay, so I think that is clear because I'm not getting any response. All right. Okay. Um. All right. For a while, class. I'll give you an overview, class. Okay. So this is again an overview. We have a question here. I'm not really sure. For a while, ha. Going back, we have an overview of the inverse matrix here, but I want to extend siguro the overview to a more para a more relatable, more or another example siguro. Okay. Um, supposing that we have this one here. Okay. So I'm giving you an overview of what we will do next after the reading break. Uh, let's just say that we have an inverse already. So we have inverse A here. So that would be A -1. And it is equal to this one here. It's 1/52. So, okay. I did not introduce this one to my Econ 106 class, but I think we still have time. We have, let me just, great. So what I'm doing right now is to give you again just an overview of class of what an inverse matrix is. So we have, but then again, we can go back to this one later, but we know how to solve for a determinant already. Okay. So let's just have. Okay, so class, here's an overview. Again, here's an overview of what an inverse matrix is and why it's useful in solving the values for X. So there are still a lot of processes that we still have to discuss, but I am parang forwarding, going to the end part of that process just to give you an overview again. So supposing class that we already solved the inverse of the coefficient matrix, supposing that this is our inverse already, and let's just say and we have already solved our determinant. So again, uh, we need to, there are methods that to be discussed on how to solve determinant of what a determinant is. But let's just say natapos natin yung discussion na yon and we have 52 as our determinant. So if the determinant is equal to 0, we mean that the matrix has no or have no inverse. If the determinant is not equal to 0, then you get an inverse. So in this case, our determinant is equal to 52, and therefore we have an inverse. So supposing class that um, we are solving for our x values here. So we have three x values. We have x1, x2, and x3. We have um, we also have our determinant multiplied to our inverse, and this is our constant. So again, we have the inverse of A, and remember class, this one here, in order to get the value for x star x star, we need to multiply our inverse with that of our constants. So in this example, we have our inverse multiplied to our constants, and we get a value for x. So let's discuss this one brief, short, ng mabilis. Okay. So in that case, what is the value of x1, what is the value of x2, and what is the value of x3? Let's try to solve this one. So that would be first, as you can see here, multiply it to the determinant, multiply the inverse to the constant. So either way, you can arrive with an answer. We can first start with multiplying every element. this scalar. So 1 over 52 multiplied to every element of the inverse matrix. So that's 1 over 52 times 18 times negative 16, negative 10, negative 13, this and that. After multiplying, you also multiply it to the constant kasi nga um I'll just kasi nga this is how we will get the values for x star. Okay. All right. Now I will use this one as a guide. Okay. This is how we will solve for x star here. Inverse multiply to the constant. Therefore, this would be equal to 2, 3, and 1. Meaning that just by multiplying the inverse here and the constant, x1 is equal to 2, x2 is equal to 3, and x3 is equal to 1. The reason that we're doing inverse matrix, other than the one I mentioned last time, is this is a method far more appropriate. Kasi if we are dealing with 3 equations, 4 equations, this and that, it would be hard to just use elimination or substitution method, diba? So you will need to do a matrix method just to get the values for x1, x2, and x3. So later on, you will have parang a lengthy process. I would say a more enjoyable process of getting the inverse once you have an idea how to determine the determinant. But again, supporting this one on how or establishing this relationship on getting the x star, then we can go through this process. Okay. Question before I go to chapter 5. None? All right. So if there's no question of what an inverse is, I'll go to chapter 5. Okay. So for chapter 5, we have linear models and matrix algebra that is continued. This part already discussed the determinant, the rank of the matrix, linear dependence, and also Kramer method. We also have other methods just to get the x star here. Okay, let's start first with the conditions with what singular case and non-singular case mean. When you have a singular case class, the thing to remember there is that there's no solution or have infinitely many solutions. Singular case, we're not really keen about getting this one, but we pay attention that the case that we're handling might be a singular case because again, determining a set of solutions, a unique set of solution is what we're after. So if it is a singular case, it has no solutions, or if you get a solution, it will have many solutions. We have a non-singular case, there is one solution. So if you have non-singular case, it means that it is a unique, it's a unique solution. What are the conditions for non-singularity? So when we say non-necessary condition, it means that there is squareness. Squareness class, that just means na there is the same number of equations as a known, and squareness is not sufficient, is not a sufficient condition for the existence of an inverse. Let's talk about linear independence. So when you talk about linear independence class, it means that, or it precludes the inconsistency and the linear dependence among the equations as well. So when we say when you have equations that are linearly independent, it just means that you can get a solution. If you have linearly dependent, it means that you will not get a unique solution to your equation system. How will we determine if those are linearly dependent? one vector is a combination of the others. I think we had a discussion with this one last time, but I think we can extend that discussion uh, to the effect of linear dependence. Okay. If you're doing graphical analysis class, it's easy to see, especially in a three-dimensional space, wherein two vectors are dependent if they lie on the same plane. We have three vectors that are dependent if they lie in the same line or in the same plane here. But the method that we'll be doing now is probably two methods. The one is a more basic one, and the other one is what we call echelon method. Okay. Now, let's have an example class on the effect of linear dependence. Now, for this part of the discussion, the situation is the situation is linear dependent. Okay, anong mangyayari pag yung equation natin or yung coefficient matrix natin or yung rows and columns natin is linear dependent? Next meeting, the assumption there is already that all of which we have already parang filtered, no, not filtered. We've already have assumed that it is linearly independent, and so that means we'll get a solution. So in this case, muna, this is the part that again, you will not get a solution value. Okay. So for a while, let me just state where is that. All right. Now, you have a matrix A here with a 3x3 dimension, and we have also transformed that one into a vector, to a row vector. Okay. So we have 3 rows. We have 3, 4, 5 as your first row, V1 prime. We also have our second row, 0, 1, 2, V2 prime. We also have our row 3 or V3 prime, and that is 6, 8, 10. Okay. Now, if you look closely, class, linear dependent tells us that there is there is one row that is a linear combination of the other two. Okay. To make the discussion short, let's look at row 3 and row 1. So row 3, you have elements 6, 8, and 10. You also have row 1, which is 3, 4, 5. But by looking for that scalar, which is again by a trial and error method, for that scalar, we know that this row is a multiple of the first row, okay, by a scalar 2. Okay, we can also rewrite this one into this. Write this one to V3 prime, so that's 6, 8, 10 equal to 2V1 prime, so that's this one here, plus 0 V2 prime. So again, we have multiplied a scalar 0 to this row to support our argument that this equation would be equal to 0. So if you transform this one into an equation, 2V1 prime plus 0 V2 prime minus V3 prime, so that is third row minus that would be first row multiplied by 2 minus the third row. It will yield to a null vector. So just by looking at this one, class, or this tells us that again, the rows are linearly independent, and therefore it yields a null vector. Let's have example 1.2. So in this case, again, you can have other scalars here that could prove your point. But so in this case, we have we have a matrix A, 2 by 2 dimension. So it's 10, 4, 5, and 2. We've also transformed a column vector to a row vector. So that would be x sub 1. X sub 1 prime, which is equal to the row 10, 4. We also have x sub 2 prime, which is equal to 5, 2. So again, you can use scalar 2 to prove that this is a multiple of the other vector by, again, a scalar 2 here. So doing the same exercise as this one, it would give you a null vector. And again, what do we mean by what what happens again with our earlier discussion? What happens when vectors of the coefficient matrix are linearly dependent? You will either get no solution or you get an infinite number of solutions. Again, pag linearly dependent yung equations natin, class, either you get a solution or you do not get a solution at all. By checking at this part of the process, yung parang before solving for x star here, you will need to check for linear dependence or independence, or before going to the process, you will need to check linear independence first para you would know that am I getting a solution? Am I not getting a solution? Para it would save your time and effort as well. Okay. Um, what else? Great. So I think what else? Linear dependence and independence. I think that one is straightforward. Great. Now let's have example number 2, class. Now, just by looking at this matrix, which has a dimension 3 by 4, um, it's a bit difficult to learn. I mean, to say if it's linearly dependent or linearly independent. Kasi nga, the matrix has more dimensions than we're used to with a 2 by 2 and a 3 by 3. So we will need to introduce later on with what we call an echelon method. Okay. But without using the echelon method, class, it is still possible to get this one just like what we did here. But again, it will take more time. Okay. But as a summary of why this is a linearly dependent or this matrix has a linearly dependent rows and columns, we can check that the first the second column is 3 times the first, and row 3 is 2 times row 2 minus 5 times row 1. So just to put that one, just to show, would it yield a null vector? Then we can have this, we can simplify by using this equation. So v3 prime minus 2v2 prime plus 5v1 prime equal to 0. And if you solve that one, class, with what what we have analyzed here, you'll get a null vector. Okay, but the idea here is quite the same. That again, by a trial and error method, looking for those scalars that would give us this argument here, or it will support this one, that would it would give us a null vector. Then still it is still time consuming. Okay. Do we have a question about linear independent dependence, class? So yung in-establish natin muna is how or what will happen if it is linear dependent. So pag linear dependent, your equations are inconsistent. You will not get an answer. If you have get an answer, and you have infinite number of solutions, or if you have many solutions. Okay. So just to go back, for the conditions of non-singularity, when we say necessary condition, it means squareness. It has the same number of equations as unknowns. It is an n by n. That is not necessary condition, and it's not enough to say that you'll get an inverse of that matrix. The coefficient condition that you would need to that is required is linear independence. So those preclude the inconsistency and the squareness. For a while, let me just clarify this part here. So it precludes the inconsistency and the linear dependence among the equations as well. Okay. Taken together, class, therefore, the dual requirement of squareness and row independence in the coefficient matrix is a tantamount to the conditions, or it's integral to the conditions for the existence of a unique solution. So if if you're very much concerned of getting a unique solution, you need to have these two conditions established. It should be a square, an n by n, and it should be linear. There should need to have a linear independence. All right, question? None? All right. What else? Let me just go through. Now, if there's no question for that, let's go to what we call a rank of the matrix. So when you see rank of a matrix, that is the row independence is only applicable to any m by n rectangular matrix. Now, the rank of a matrix class, this is the maximum number of linearly independent columns and rows. So whichever is the minimum there. So if you have a dimension that is mm by n, whichever is smaller, for say for example, if you have a 1 by 2, the rank would be at 1. Again, whichever is smaller. Okay. Now for a given matrix class with only 2 rows or 2 columns, or let's just say a 2 by 2, okay, row independence is easily verified by visual inspection. Just like we just need to check whether one row is the exact multiple of the other. So pag ganito class, pag ganito, if it's only by 2 by 2, you just only need to check one column if it is a multiple of the other. But what gets more complex is, again, if you have a 3 by 4, if you have a 3 by 3, or if you have a matrix of larger dimension. So again, we will need to have or we'll need to use an echelon matrix by using certain elementary row operations. Okay, and these are those operations. The first one is we interchange the rows. The second one, we add a multiple of one row to another. Number 3, we multiply a row by a non-zero scalar. So how do we use an echelon method? Let's have this example, okay? So we have matrix A here. Dimension is 3 by 3. We also have an identity matrix and a 3 by 3. So what we're doing with an echelon method class is we are transforming this matrix into an identity matrix. Again, what we're doing with this echelon method is by using this elementary row operations, we will transform this into an identity matrix, meaning that this would be equal to 1, 2 would be equal to 1, and 9 would be equal to 1, and the rest of the other matrix or 0 elsewhere. So how do we transform this into other matrix? It's a trial and error method again. So when I say trial and error method, there are so many ways that you can do this one. But what we are doing with an echelon method is just to determine what is the rank of the matrix, or what is the non-zero, how many non-zero rows of that matrix. Okay, so all right, let's start. So for this example, let me just clarify this one. Okay, so again, transforming it to an identity matrix, we have a 1 there, so we can easily swap. We can just swap it. Okay, so we can swap 1 to 4, or the whole row. So everything that I perform here, I perform it together with the other elements in the row. So that is 1 row here, transform it this one. So transform, that is 1, 2, 3, 4, 5, 6. Okay, question. Again, if you have questions, raise your hand or unmute yourself. If not, I'll just go all the way. The next thing to do is just follow this Coursera class. So the next thing to do is we already have 1, 2, 3, 4, 5, 6, 7, 8, 9. The next thing to do is we make this one as a 0. Okay, I'll just have this one quickly as a guide. Okay, I know you already know what an identity matrix is, but it's good to have a guide on the side. Okay, so eto, we're transforming this again, this matrix into an identity matrix. So we're done with 1. We'll have, let's make this one as 0. Okay, So how do we make this one 0? We can, again, you can have many solutions, or no, you can do this in any other form class, but I chose this one here. So we have, um, how do we make this one 0? Negative, we introduce -7. Okay, so that would be -7, multiply it. So we have a scalar -7, and we multiply it to the first row. Okay, so we have -7. Oh, okay. Okay, so going back, how do we make this one 0? We have a negative scalar 7, and we multiply it to every element in the first row. So that would be -7 times 1. That would be -7 plus 7. So have a scalar 7, multiply it to every element in the first row. After that, you add it to the third row. So -7 times 1 plus 7, that would be 0. -7 times 2, we have -14. -14 plus 8, we have -6. We have -7. -7 times 3, we have -21. Plus 9, we have -12. Question? Okay, so right. Now, when we're done with this one class, it will look like this. Okay, or parang it would look like this. It would this would be the next part of the echelon method. Okay, so we have 1, 2, 3, 4, 5, 6, 0, -6, and -12. Okay, all right. Now again, we're done with 0 here. We need to have a 0 also here. So may we make this one 0? How do we make this one a 0? We can have -4 again. So -4, a scalar -4 times this row here, and add it again to the second row. So let's have -4 times 4. No, -4 times 1. That would be -4 plus 4, 0. -4 times 2, we have -8. We have plus 5, we have -3 after. -4 times 3. Okay, so when you have -4 times 3, we have -12 plus, yeah, we have, hmm, for a while, -6, -4 for a while. Let's resume. So again, we are already in the part of multiplying a -4 scalar to this row and adding it to this row, and then it will look something like this. Okay, so it will now be 1, 2, 3, 0, -3. We now have -6. We also have 0. We also have -6 and 12. So as a guide again, we can, yeah, as a guide again, we can have we can have an identity matrix. So with our current matrix here, we have 1, 0, 0. We'll need this one to make 1. Okay. So how will make this element 1? We can multiply a scalar -1/3 to, yeah, we can multiply, let me just check against tasa, -1/3 times -6. All right. So how will we make this one as 1? Again, following this, we'll introduce a scalar -1/3, multiply it in every element in this row. So that would be 1, -1/3 times 3, negative 1 over 3 times negative 6, and it will look like this. So that would be 1, 2, 3, 0, 1, 2, 0, negative 6, and 12. Okay, so the next thing to do is to have, how are we, that 0, yeah, 1, 1. We'll make this one a 0 class. Okay, how will we make this one 0? We introduce a positive, let's have positive 6, a scalar positive 6 multiplied to this row here and added to this third row here. So let me just check. So we have a positive 6 multiplied by, again, every element in the second row. So that would be 6 times 1, positive 6. Add that to the third row. So that would be 6 minus 6, that would be 0. 6 times 2, you have 12. Plus negative 12, you have a 0. So you'll end up with this one here. Okay, we can stop already, because again, if we will have to make, if we will proceed, continue, we might have another, if we'll continue with 0 here and 0 here, this might not be a 1 anymore. Or if we continue with getting a 0 here, this might not be a 1 anymore. So that is a cue for us to already stop the process. Now, what this tells us, class, the rank, again, by definition, counts the number of genuinely independent rows. And if it has its only 2 by 2 dimension, or if it's the dimension is 1 by 3, just check on whichever is smaller. If you have a larger dimension, like a 3 by 3 here, you will need to get an echelon method. So the rank for this matrix is the number of non-zero in the matrix. So when you say non-zero, may dalawang, the first row is a non-zero, the second row is a non-zero, the third row is a 0, is 0 in the matrix. Therefore, the rank of this matrix is equal to 2. Question? So I'll stop the recording now.